I'm going to talk today about evaluation metrics, and I have two reasons for that. One is that my own background, how I came into machine learning, was from a different industry, from software development, and so I had to learn a lot of the things on my own, and machine learning metrics was one of the topics that was a little bit confusing because there were tons of them, and how are they different? When should I choose which one? So I had to Google a lot, and if you are like me, entering the field from a different background, I'm hoping to save you some time, and so I hope to summarize what these are and how you can use them. And another reason for this talk is that evaluation metrics are something that you use to ultimately decide which machine learning model you're going to use in production, which model is going to be used in real world, affecting decisions, affecting sometimes human lives. And this is a metric that you rely on. So it is, in my opinion, essential to understand how they work, what's the difference between them, so because you're going to be using it as a tool in your work a lot. So what's an evaluation metric, just so we are on the same page? Evaluation metric is a way to quantify performance of a machine learning model. So when we train a machine learning model, we don't want it to simply memorize the training data. We want it to be able to generalize. So we want it to be giving good predictions on the data that it has not seen, and we need a way to quantify that. So we usually don't train just one model. We tune hyperparameters. We try different algorithms. We try different maybe sets of features. And then again, we need to compare the performance of all those models and choose the one that we're going to use. So now we know what it is and why we need it. There are different techniques of evaluating the machine learning model's performance, but high-level idea is that you somehow train the machine learning model on one set of data, and you keep another set of data that the machine learning model did not see, so you can evaluate that performance. And you can have holdout or train test split technique, where you essentially split the data in different chunks, and there are also different approaches to that, randomly splitting or keeping the last in time data for the test, and there are many techniques to do so. If you don't have that much data, you may need to do cross-validation, and it is essentially kind of like a repeated holdout when you just split the data, train, evaluate, split again in a different fashion. Train, evaluate again, and then average the metric. There are also different ways of choosing an optimal set of hyperparameters. There's a straightforward grid search. There is typical there are different optimized algorithms and tools like HyperOpt, for example, to choose over the space of hyperparameters. But then again, ultimately, you're trying to find the one model with certain set of parameters that are going to give you the best value for the metric that you have chosen. And in this talk, I'm going to talk about supervised learning metrics, and these are the ones that I'm going to cover. There's more, but these are the ones that I consider essential, and these are the ones that are most commonly used. And as you know, in supervised learning, there are two categories of problems. We have classification and we have regression problems, and they have different sets of metrics. And I'm going to start with classification metrics. And to make things a little bit simpler, first we're just going to limit this to binary classification. That's where you decide whether the picture is of a hot dog or not hot dog, if you're familiar with the reference. So the first metric you normally will encounter is classification accuracy, of course. And it is very straightforward. It's very intuitive and easy to understand. So how many predictions were correct out of the whole number of predictions? And I'm going to be showing examples in scikit-learn, but any machine learning any machine learning library is going to have its own set of metrics available to you. And in scikit-learn, let's say I trained some simple logistic regression on some data, and there is a score method that that's going to give you the accuracy as a default evaluation metric for any classificator in scikit-learn. So in this case, I get 96% accuracy, and it may seem great, but except from this example, we don't know really if it's a good accuracy or not. And to illustrate this, I took the same data and I trained a dummy classifier on the same data. In scikit-learn, a dummy classifier is a classifier that doesn't learn anything from the data, but it follows some strategy. In this case, let me see if I can, oops, does something wrong. Anyway, in this case, my strategy is to predict always the most frequent label in the training data. But there are other strategies too. You can, for example, generate predictions uniformly at random, and there are two, I think, more strategies there. And I can use dummy classifiers as a sanity check, and they have all the same, let's say, methods and properties like regular classifiers. So I can, for example, use a score method on it, and I get 94.2% accuracy. And this is not, it seems like something was really wrong with my model because it only was doing a little bit better than a dummy classifier. And the reason is in the data, of course. I simply generated this data with 10,000 examples where only 5% are of the positive class. And this is what is called a class imbalanced data set. And these are quite common. Whenever you're classifying some rare events, you're going to have more examples of the normal events or normal examples, whatever that may mean. And in this case, accuracy is going to give you false impression that your model is doing amazing, when in reality that may not necessarily be the case. So while it's very easy to understand, it may be confusing, and accuracy alone will not help you. Will not help you diagnose the errors that your model is making, and it's not going to help you address those errors. But of course, we have a lot more diagnostic tools and other evaluation metrics. And I'm going to start with confusion matrix, which is not a metric, but it's a very useful diagnostic tool to gain insight into the type of errors your model is making. And it also is useful to understand how other metrics work, because we can get them from the confusion matrix. So this time I took Titanic dataset from Kaggle, where the goal is to predict survival of the passengers, skipping all the data cleanup and feature engineering, skipping all the work. Here's a basic random forest classifier. It gives me 83.4% accuracy. And I can import confusion matrix from scikit-learn.matrix. I can give it the test data and the predicted values from this model. And then I get back this beautiful array with numbers. If, for those people who see it for the first time, it can be confusing. What does it mean? So typically, people illustrate confusion matrix. They draw it as a table like that. It makes it a lot easier to understand what's going on here. So by convention in scikit-learn, and it is the same in TensorFlow and some other libraries, you get the actual true labels in the rows and the predicted values labels in the columns. But there are different libraries that have it the other way around. So if you're reading some articles and you're looking at results, be careful and take note of what the convention with that specific library or in that article is, because it can be, you can be seeing one thing, but it's actually a different thing in there. So what can we get from this confusion matrix? Who doesn't know what false positive or true negative is? Nobody. Perfect. So this is what we can get from the confusion matrix, and we can also get the accuracy from it if we just sum up what's on the green diagonal and divide it by the sum of everything in all the cells. But there are other metrics that we can get from the confusion matrix. And let's start with an example. Let's say we are building a classic example, spam filter, in which case spam is a positive class, and we want to reduce the number of false positives, because a false positive in that case means that I have a very, very important email about my promotion maybe, and it goes into the junk folder, and that makes me really unhappy as a user. So fishing out important emails out of a spam box is not a good user experience. And there are many examples of that, typically when it's something user-facing system, recommendations that are not relevant to you, and that sort of thing. So in this case, I want to have as many false positives as possible. And there is a metric that can help me with that. It's called precision. The formula is very simple. It's the number of true positives divided by true positives plus false positives. And as you can imagine, the smaller the number of false positives, the better the metric. Now, if on the other hand, we care about false negatives, we only want to, so we, for example, predicting a cancer diagnosis or something like that. And it is safer to send a person who is healthy to take a few more tests than to miss that diagnosis and send a person home. The risks are higher here if we do not predict this negative outcome. So in this case, there's a very, very similar matrix called recall that allows us to focus on the false negatives. And it works the same way. You have less false negatives, the metric gets better. The one tricky part about these two metrics, at least for me as I was starting in machine learning, was to remember which one's which. And to me, what it helped to think of that precision starts with P, and it's all about positives, true positives, false positives, and recall is the other one. So I hope that maybe will be helpful to someone else too. And then, of course, we have another way of summarizing the confusion matrix in one metric, and it's called F1 score, that allows us to take into account both precision and recall, and it's essentially just a harmonic mean of the two. So when you're choosing a metric to evaluate your machine learning model, not only the shape of the data is important, but also what is your business problem? What are the important types of errors that you maybe want to put more focus on? So if you care about minimizing false positives, you may want to monitor the precision of the models. And if you care about minimizing false negatives, then you need recall. So a lot depends on the data and on your business problem. In scikit-learn, we can get these metrics from the same module as confusion matrix, so scikit-learn.metrics. And then for this particular case, I get different precision, recall, and F1 score. And if I want to search through hyperparameters, for example, with a grid search, I can easily do this, and I can say I want to find a model, find hyperparameters for this model that will give me a good recall, the best recall. And you can do this by specifying scoring parameter for the grid search. And in this case, I got a small improvement. Accuracy and F1 score are not the only ways to summarize a confusion matrix in one metric. There is also Matthew's correlation coefficient. How many of you are familiar? All right. it's another way to summarize the matrix. And this is the formula. The only thing I want you to notice about this formula is that it takes into account all 4 cells of the confusion matrix. And that has important side effects. Let's compare it with F1 score. First, I'm going to take the very, very artificial example. I have my data of 100 samples, 95 of them positive, 5 negative, and I have a dummy classifier. So accuracy is going to be 95%. I'm always predicting that it's positive. And this is what F1 score is going to be, just doing the math here. And it's actually even a little bit better. But if I try to calculate MCC, scikit-learn is going to give me a 0 and a big red warning because I'm dividing by 0 and it's undefined. And it's so far the only metric that is giving me any indication that something's wrong going on here. But you can say, hey, well, you know, it's a dummy classifier. It's not a real thing. So how often is it going to happen? OK, let's take a different example. So now I have the same data, but I have a slightly better model, and I managed to predict I have some true negatives, some true positives, some false negatives and positives. I get F1 score, a little bit lower. I get MCC, 0.135. But what I'm going to do now, I'm going to say, so what I was calling a positive example, I'm going to call a negative example, and the other way around. So I'm just going to switch what I call a positive class and what I call a negative class and calculate, and the model is the same, the predictions are exactly the same. What happens is, so the confusion matrix is going to be a little bit different, but the model is essentially still the same. MCC stays the same, but F1 score changes drastically. And this is exactly because MCC takes into account all 4 cells of the confusion matrix, while F1 score, it's a harmonic mean of precision and recall, and neither precision or recall take into account false, which one? False negatives, right. So that makes F1 score very sensitive to what you call a positive example and what you call a negative example. And all things considered, I find MCC to be a better way to summarize a confusion matrix when you have a binary problem. Unfortunately, it's quite hard to extend it to a multi-class problem. So there are limitations to that. But so far, we've looked at metrics that only take into account whether prediction was correct or not. But of course, a lot of classifiers, they output probabilities of a sample belonging to a positive class or to a negative class. And there are, of course, metrics and diagnostic tools that take that into account. So one of these things, one of the diagnostic tools is ROC curve, and ROC stands for receiver operating characteristic, which doesn't help to understand it. But what it is a plot where on the x-axis you have false positive rate, and on the y-axis is a true positive rate. And before I was talking, so a model has 1 precision, 1 recall. Why is it a curve? That's because we have probabilities. And when we have probabilities, we have a certain threshold where we decide we're going to label it as a positive class, or we're going to label it as a negative class. And we can move that probability, that threshold, and say we are going to only classify the sample as a positive class if the probability is higher than 90%. So what we can do here, we move this threshold, and for each threshold, we recalculate the true positive rate and false positive rate, and then we get all these dots, we get this curve. And we want it to be really, really close to upper left corner, because if you think about it, if we have a threshold, some threshold at which we perfectly classify everything, then the false positive rate is going to be 0, true positive rate is going to be 1, so it's going to be in that upper left corner, and as we move the threshold, we're going to get the lines along the upper boundary and the left boundary. But this is not a number. So we cannot really, we can visually inspect different models, but for a metric, we need a number. And we can get the number very easily. AUC stands for area under curve. It's essentially how much of this box is under this curve. And if you have a really good, perfect ROC, it's going to be 1 because it's going to be the whole box. So that's not the only curve that you can use. There's also precision recall curve. And this is a very similar thing, except now on the axis you have precision and recall. How are they different? Well, it comes back to imbalanced data. So the same example with class imbalanced data, we take probabilities and we plot both curves. And as you can see, ROC gives me a score of 0.92, when precision recall curve is going to give me only 57.7%. So again, when you're dealing with class imbalanced data sets, ROC curve may not be ideal, and you may want to add some other metrics or maybe look at precision recall curve instead. Of course, there's also log loss. And this metric is good because it takes into account the probabilities. And it is also often used both as a loss function and as a valuation metric, which is great because that's something that you're already optimizing for. So a loss function takes into account the uncertainty of model predictions, and it penalizes wrong classifications, but more importantly, it gives higher penalties to predictions that are not only wrong, but also very confident in their predictions. And it is, I would say, very close to accuracy in the sense that when you minimize the log loss, the accuracy is going to be increasing too. So this is what it would look like on a very, very simple example. So we have a label, a true label, the predicted probability of class 1, and the log loss. So as you can see, if the true label is 1 and predicted probability of the sample belonging to class 1 is very high, the log loss is quite low. But the more wrong the model is and more confident the model is in its predictions, the log loss tends to skyrocket there. But just like the accuracy, it gives equal weight to all the samples. So again, in class imbalanced scenario, you may want to add some more metrics here. Now, how do these extend to multi-class scenario? You still can use confusion matrix. In this case, you still, it's better to visualize it because it becomes a lot harder to understand what's where. And you still have true labels on the rows and predicted labels on in the columns. In this case, it's a digits data set, so numbers from 1 to 9 are actually the labels. And you still get the diagonal with the correct predictions, but now you can actually see what labels were misclassified for what and diagnose and maybe look into those samples. But now we don't really have the notion of true positive and negative. It's no longer a binary problem. But we can calculate metrics such as precision, recall, and F1 score. To do that, we need to treat the problem as a collection of binary problems, one versus all. We calculate these metrics per label, and then we average them. And as you can see, there are different ways of averaging. So you get macro averaging, micro averaging, and weighted averaging, and you're going to get different results, even on this very, very simple example. So what's the difference between these ways of averaging? Let's take this example. First, I'm going to convert it into a confusion matrix. Now, for this confusion matrix, I'm going to write down the numbers of true positives and false positives. I'm only going to do precision because the other ones are going to be exactly the same. So for the class bird, True positives are every time when it was a bird and we predicted a bird, so only that one cell in the corner. False positives are going to be all the times when we said it was a bird but it was not, so everything in that column except for that cell when we were right. So we sum it up. And well, false negatives would have been every time we said it was not, it was something else, doesn't matter what, but it was actually a bird. So it would be this whole row summed up without that cell. And we do it for each and every class. In the end, I write down the total numbers of true positives and false positives. Now, I can calculate precision for each class individually. So for the bird, it's going to be 1, for the cat, 0.8, and so on. I'm also going to add here the number of samples. And now, micro-precision is going to be calculated just from the totals. So in this case, all the samples get taken into account in equal manner. Macro precision is going to be simply the average of per class precision. In this case, every class contributes equally to the metric. It doesn't matter how big or small it is. And the weighted precision is calculated by taking into account the sizes, so the number of samples within each class. So we get a slightly different metric. So which one do you choose? Again, micro-average. Every sample equally contributes to the average. And macro-average is when all classes equally contribute to the average. Weighted average is when each class's contribution to the average is weighted by its size. So for example, if you have, again, class imbalance data set, and if you have some classes that are more important to get right, you may want to go for a macro average to amplify the contribution of underrepresented classes. Scikit-learn documentation recommends using micro-averaging for multi-label problems. And in other cases, you can also go for weighted average. There's, of course, also multi-class log loss. And it is a broader case of a binary log loss. In fact, it's actually the other way around. The binary case is a subclass of multi-class log loss. If you're like me, coming from software background, and looking at this formula and thinking, like, what's that? It helps to think of it as a for loop. So I wrote it down here as a for loop. Essentially, we take, for each label, we take a binary indicator, whether it's the right label for this sample, and then multiply it by the log of probability of this label being the right for this sample, and then we sum it up. Of course, in scikit-learn, there's a different implementation, vectorize and optimize and all that, but just to understand how it works, for me, for example, it helps to think of it as a for loop in a for loop. Now let's switch to regression metrics. I find that regression metrics are a lot easier than classification metrics in the sense that you don't have multiple possible versions of an answer. We're only dealing with continuous value, and we don't have probabilities to deal with, so it gets a lot easier. We just have continuous value, we have predicted continuous value, we subtract one from the other, we get the error or residual, and now we just need to figure out a way how to use all individual errors and combine them into one metric that's going to give us the idea of what's going on. In scikit-learn, all regressors have a default scoring method, default evaluation metric. So if for classification it was accuracy, and for regressors it's R squared. R squared indicates how well the model predictions approximate the true values, where 1 is a perfect fit and 0 is a dummy regressor predicting the average. And this is how it's calculated. So 1 minus this scary thing. In the numerator, you essentially have all the squared errors summed up. And in the denominator, the sum of square distances between the actual value and the mean of actual value. So if you have a dummy regressor, the top and the bottom are going to be the same. You're going to have R squared of 0. You can go into negatives as well if you're predicting really, really large numbers which are make no sense at all. The good thing about it is that it has intuitive scale similar to accuracy, kind of like a percentage value. And it does not depend on the units, whether it's prices, distance, whatever it is, it doesn't matter. But it also doesn't give you any information about the predictive error. And for example, if it's prices, your stakeholders probably care about how many exactly dollars this is going to be and what's the prediction error. But there are metrics, of course, that are going to help you with that. The first one, the easiest one, is the mean absolute error. It's essentially just the mean of these absolute errors. It's very straightforward. It's linear. And then we also have mean squared error, very similar to absolute instead. Now we just square the errors and take the average of that. The only thing with this metric is that it's gonna, if you have a large error, it's gonna square it, so it's gonna be huge. And this is not always desirable. So that's why we have root mean squared error. And it's also often used as a loss function. So this is just mean squared error, and you take a root out of this. This is one of the most commonly used metrics, but every now and then people are asking themselves, so is it a good metric, or maybe we should do the absolute error, because there's, we're squaring the error, so how adequate is that? And they do have a lot in common. They range from 0 to infinity. They have the same units as y values as the targets. They don't care about the direction of the errors, and you want this metric to be as low as possible. But there are differences. RMSE gives relatively high weight to large errors, and mean absolute error is more robust to outliers because it doesn't square the errors. RMSE is differentiable, but it doesn't really matter in this context because we are not applying this during the training. We're only applying it afterwards. And I've seen a lot of articles arguing about which one is better. I think the ones who say that absolute error is better based on the paper from 2005 by Wilmot and Matsuura, they argued that RMSE is an appropriate and misinterpreted measure of average error. But then, 4 years later, there was another paper that said that actually that's not the case, and RMSE is perfectly fine. In all the practical cases, RMSE is actually a perfectly valid metric to be used. But, the older paper sometimes still gets quoted. But neither of the metrics is going to be robust on a small test set. So if you have very few examples, none of them is going to make for a robust metric. Sometimes I also use this one, a version of RMSE, root mean squared logarithmic error. And it's very similar to RMSE, but it uses natural logarithm of y plus 1 instead of y. Plus 1 is just because the log of 0 is not defined, and it shows relative error, and it helps with scale. For example, you have, again, prices. You have $50 prices, and you have $50,000 prices. $5 error is going to be very, very different for these two different examples. So you want to scale that. So, and log helps you do that. So it's going to be very, very useful. You can scale the targets as well and then use RMSE, or you can use this metric, so one or the other. This metric tends to penalize under predicted estimates more than over-predicted. That depends on the context if you want. Normally, I haven't seen an example where it mattered too much. One metric I want to show you that business people really like, and this is mean absolute percentage error. This one shows, well, essentially, your error, what percent of the actual value it is on average. And this is just very easy to understand. In the presentations, business people tend to ask about this kind of thing. But it's very problematic if you cannot use it if your targets can be zeros, because you're dividing by 0 in this case. And it has a lot of issues when the targets are really small. So you have to be careful with it. But sometimes it comes in handy. And before I'm going to wrap it up, I'm going to give you a couple of warnings. And these are, any metric is going to be only a proxy to what you really want to measure. And we've seen examples of when a metric is not necessarily the best choice, when you decide that the viewers of your video content are going to be happy if they watch more, and then you see the rise of conspiracy theories, promoted weird content, and that sort of thing. So how you define success, how you choose what you measure, and that's going to affect also the metric, and you have to be conscious about that. And another thing is metrics can be gamed. So in the keynote yesterday, the keynote speaker mentioned that they're considering the ways how they can game the Spotify algorithm to get their clients show up on the playlist. And everywhere a system is, or everywhere possible, really, if people are going to try to game metrics. And there were some also political news around that too, when some content from specific countries showed up in their algorithms higher than the content from trusted sources, let's say. So metrics can be gamed, and they're not the ultimate truth for everything. So that's something to keep in mind as well. Now, there's no one metric that's going to fit all your cases. You have to be careful which metric you choose depending on your data, depending on your business objective and what exactly you're trying to optimize for, what your success looks like. And as with everything else, you need to apply common sense, and where possible, invite domain experts who are going to be able to give their opinion on whether your metric actually makes any sense in this particular context. I'm going to publish my slides on Twitter, and I have a bunch of links in there if you want to read some more. And if we have time, I think I can take some questions. Thank you.
So I was wondering if there are metric ensembles, like the way there are model ensembles.
That's a good question. Well, I guess, well, you certainly could do this, but you would have to be, like, you could do that on your own, and you would have to define how some metrics may be way more or less. I don't think there is a kind of a standard approach to this, so that may make sense under some circumstances, but that would be very specific to whatever you are trying to do. So I'm not aware of standard techniques for that, but you could do that. Just like try to figure out how would you do this? And then the problem with that, it's going to be harder to interpret than each individual metric on its own, that's for sure. And whatever logic you built into that, you'll have to unroll that when understanding what's happening. I don't see any hands, okay, so I guess, thank you.
All right.